Okay, class, welcome back, and today we're going to continue on, and we're almost to the end. So today we're going to talk about applications of other types of equations. Okay, so other types of equations and applications in this section. And so we're going to talk about rational equations, work rate problems, equations with radicals, equations with rational exponents, and we're going to talk about equations that are what's called quadratic in form. Okay, so that's what we're going to tackle today. Okay, so what is a rational equation? It's an equation that has rational expressions of one form or another, of one more or more terms. So basically, what is a rational expression? A rational expression, as we've talked about in the review part, is a fraction, right? It's a rational expression is an expression, it's an algebraic expression that is in fractional form. Okay, now, to solve a rational equation, you multiply each side by the least common denominator, LCD, of the terms of the equations, and then we solve the resulting equation. Okay, now because a rational expression is not defined when its denominator is 0, the proposed solutions for which any denominator equals 0 are going to be excluded, or a restricted value. Okay, they're excluded from the solution set. Okay. So if we look at this one here, we want to solve this equation. Okay. So what do? We want to solve by multiplying first and getting rid of these rational expressions. We want to get them into looking like a regular polynomial. So we want to multiply by the least common divisor. Well, the least common divisor is going to be what? It's going to be the multiple of both of these, right? Because they don't have anything in common. So it's going to be 3 times x minus 1, and that's what we're going to multiply by. And that will get rid of the 3, and that will get rid of the x minus 1 here. Okay. Now, we also have to remember that if x is equal to 1, we get a 0 here. And so we know that right away, x equal 1 cannot be in the solution. So if we end up solving this and one of the solutions is equal to 1, we cannot count it. Okay. So now we're going to multiply through by everything by this common divisor, the lowest common divisor. And so now what's going to happen? Well, this is going to cancel with the 3. This is going to cancel with the x minus 1. And we end up with this. Okay. Now we can start multiplying using the distributive property and simplifying. Okay, so here's what we have. And so now what we're going to do is we're going to add like terms and start solving and put it into standard form. So this is going to give us negative 10x, and then we're going to move all of this over so that it's in standard form. Okay, so here, we get a 3x squared and a 3x here, so that goes away. So it ends up canceling out. And so what do we end up with? We end up with 1 minus 10x is equal to minus 3x, okay, or negative 3x. Okay. And then, of course, we move this over here, and that gives us 7x, and that gives us a 1. So we get 1 equals 7 times x, and we get x is equal to 1/7. And this is the proposed solution. So it's not 1, so it's not in the restricted domain, right? So it meets the requirement of not being equal to 1 and does not cause any denominator to equal 0. So now we want to substitute this in just to correct, check for correct algebra, just to make sure we didn't make any mistakes. And the solution set is equal to 1/7. Okay, what about this one? Well, here we're going to multiply by the lowest common divisor, which is x minus 2. And so If we multiply everything by x minus 2, then we're going to get x is equal to 2 plus 2 times the quantity x minus 2. Okay. And now we're going to just simplify. In this case here, we're just going to use the distributive property and then add like terms and solve. Okay. And so we get negative x equals negative 2, and we get, which means x equals 2. Okay. Now, in this case here, this is not going to work because remember, 2 makes this 0. So x equal to 2 cannot be a solution. So that means there are no solutions to this. And that should make sense, right? Remember when at the very beginning of this chapter we were talking about dependent and identities and contradictions. Well, look at this. This is the same here, and this is the same here, except we got plus 2. So if you want to do like a u substitution, say this is u, and this is saying u is equal to u plus 2, which is never going to be true. So this, you can see, is a contradiction, and therefore there will not be any solutions. But we just showed the same thing. Okay? So this is the empty set. The solution set is the empty set, or the null set. Okay, now what about this one? Okay, so here we've got x minus 2, x, and x squared minus 2x. So the first thing I'm going to do is factor this. You want to factor the denominators as much as possible. Because here, if you factor, you're going to get x times x minus 2, which is the same as these two. Okay, so you got them repeated here. Okay, so then the least common divisor is just going to be x times x minus 2. Okay, so the first thing we do is factor the last denominator, and then our least common divisor becomes actually x times x minus 2, since those are the only two distinct roots, or not roots, but the distinct factors there are. Okay, so now this is going to end up with x, this is going to reduce to x minus 2, and this is going to basically reduce to 1, because it's the same. Now notice that x cannot equal to 0, and x cannot equal to 2. So any one of those two values, either one of those two values are restricted. Both of them are restricted, I should say. Okay, so now we're going to start simplifying. So we use the distributive property, and then now we're going to what? Add like terms and put it in the standard form. And we get 3x squared plus 3x. And now here we can factor out a 3x. Oh, hold on a second. Yes, we can factor out a 3x. And so that's going to give us a factor form of 3x times the quantity x plus 1. And so that means x equals 0 or x equals negative 1. Okay, so here we go. Now remember, x cannot equal 0, right? So therefore this is not a solution, but this one is. And so we want to basically take the solution and plug it back in and make sure that we get a true statement. Oh, hold on a second. Okay, there we go. So now in this here, here's another one. So we've got x minus 1, x plus 1, and then we got x squared minus 1. This is the difference of two squares. So this will factor into this times this. So we got a similar situation here. So first thing we do is factor. And so now we know the lowest common divisor is going to be this. This is going to be the lowest common divisor. So we're going to multiply everything by that. But also keep in mind, x cannot equal negative 1, and x cannot equal 1. Okay. Now, what do we end up with? Well, things are going to start canceling, and we end up with this. And so again, we're going to use the distributive property. Then we're going to add like terms, and notice these terms are going to drop out. Okay, and so here we can factor out a 4. So this actually can reduce to a negative 4. We'll factor out a negative 4, and this will reduce to x squared plus 1. Or excuse me, minus 1. X squared minus 1. And then what happens now? Now you just solve, and you get what? X is the square root of 1, plus or minus, which gives you plus or minus 1. Yeah, so here I would just add 1 to both sides and use the square root property, but they don't do that. Okay. And so there's no solution to this for the same reason that the other one. Because both of those are restricted values. Okay, so now work rate problems. Okay, so if a job can be done in t units of time, then the rate of work, R, is 1 over t of the job per unit time. So it's going to be 1 over that, right? So if it takes, the rate would be 1 over t, okay, of the job per unit time. So the rate is 1 unit over t. So the rate of work is going to be 1 over t. Okay, so if it takes, let me think here. So if it takes 10 hours to do a job, okay, then the rate of doing the job is going to be 1/10 of the project per hour. Okay, so if it takes 10 hours, then you're going to have the full object, so it's going to be 1, right? It'll be finished in 10 hours. So that means if you're going at a constant rate, then you're going to have 1/10 of the project done every hour. Okay? So now, the amount of work completed, A, is found by multiplying the rate of work, R, and the amount of time worked, okay, T. So this is very similar to the distance equals rate times time formula. But now we're going to do A equals R times time, R times T, rate times time. But now we're talking about the rate at which you work times the amount of time that you worked equals the amount of work that was done. So now let's see if we can apply this. It says one printer can do a job twice as fast as another. Working together, both printers can do the job in 2 hours. How long would it take each printer working alone to do the job? Okay, so we know that it takes one printer. Okay, so one printer can do the job twice as fast as another. Together they can get the job done in 2 hours. How long would it take each printer working alone to do the job? So let's again read the problem carefully. We must find the time it takes each printer individually, how long it would take them to do the job. Okay, so let's take the information that they're in. So let X represent the number of hours it takes for the faster printer working alone to do the job. The time for the slower printer to do the job alone is then twice as long, right? So if one printer is twice as fast, that means it's going to take less time or half the time to do the same job, right? So if X represents the number of hours it would take to finish the job, and we want to do the faster printer, well, that means the faster printer time is X, And the slower printer, the time for that printer to do the same job would be 2 times x. So therefore, if we have 1 over x, 1 over x is the rate of the faster computer, right? And the rate of the other, the slower computer is 1/2 x, or excuse me, 1 over 2x. And so now the faster printer, here's the rate, here's the time. And so now what part of the job is accomplished? Well, you multiply these together and you get 2 over x. Okay, so using this formula. And then the slower printer, here's the rate, here's the time. And so you do rate times time, which is going to be this. And then so this cancels with this and you get 1 over x. Okay, and this should make sense because the faster printer goes twice as fast. So it makes sense that double whatever the amount done by the slower printer, the faster printer will be double, right? So this is 2 times 1 over x, right? Here's 1 over x, 2 times 1 over x, right? Okay, so this should make sense so far. Okay, so now remember, what's the goal? We're trying to find how long it would take each printer to do the job, the same job, separately. Okay, so now we know that this, right, the part of the job done by the faster printer plus the part of the job done by the slower printer has to equal 1, right? So again, what are we using? We're using the fact that they're working together, right? So 2 hours here, 2 hours here. It took them both 2 hours, right? So this is the proportion of the job that was done in 2 hours by the faster printer. This is the proportion of the job that was done by the slower printer, okay? So now we have to add those up, and this proportion and this proportion of the job has to equal to the one whole proportion. So this plus this must equal 1. You got one whole job done. Okay, whatever that job is. So if we add these, we've got a common denominator, so we can add these, and this becomes 3 over x. Okay, so we get 3 over x equals 1. And so, oh, by the way, x can't be equal to 0, right? I mean, for obvious reasons, x can't be equal to 0. Okay, so here x can't be equal to 0. And so now we're going to multiply by the lowest common divisor, right? And we get 2 plus 3 equals x, so x equals 3. So the faster printer will take 3 hours to do the job alone, and then the slower printer would have to take 6 hours. Okay, be sure to give both answers here. Don't forget that they're asking you for 2 answers. And then check the answer. So the answer is reasonable since the time working together, 2 hours, is less than the time it would take for the faster computer to do the work alone. Okay? Okay, now rate problem. So note, in example 3, number 3 can also be solved by using the fact that the sum of the rates of the individual printers is equal to their rate working together. Okay, since the printers can complete the job together in 2 hours, their combined rate is 1/2 of the job per hour. right? So that makes sense, right? The combined rate, it takes 2 hours to do the job, so it makes the rate, the combined rate, 1/2 of the job per hour, right? That makes sense. So we know that this rate plus this rate has to equal 1/2, okay, for their combined rate. And so if we take this and we're going to multiply by the common, the least common divisor, which is going to be 2x. And so now what happens? We get 2 plus 1 equals what? X, which is exactly where we started from. And x equals 3. So we get the same solution. Now, power properties. So let's take a look at this. Now if we have P and Q are algebraic expressions, then every solution of the equation P equals Q is also a solution of the equation P to the nth power equals Q to the nth power. Okay, so if you have P equals Q, any solution to the equation P equals Q, okay, where P and Q are algebraic expressions, okay, every solution of the equation P equals 2 is also a solution to the equation P to the n equals Q to the n for any positive integer n. So now be very careful when using the power property. It does not say that the equations this and this are equivalent. Okay? Does not say that they're equivalent. Doesn't say that all of the solutions of this equation are the same as the solutions of this equation. It's an if-then statement. If a value is a solution to this equation, then it must also be a solution to this equation. Okay? It doesn't mean that it goes the other direction. Okay? Just be careful of that. Okay, so how do we solve these equations using radicals? Okay, so one, isolate the radical on one side of the equation. Then we're going to do is raise each problem to the power that is the same as the index of the radical. So if it's a fourth root, we want to raise each side of the equation to a fourth power. Okay. Now, if the equation still contains a radical after step 2, then repeat steps 1 and 2 over and over again until you have no more radicals. Okay. After you get rid of the radicals, step 3, solve the resulting equation, and then check each proposed solution in the original equation. Remember, not all of the solutions will work in some cases. So now, let's do the steps. First thing is we need to isolate this radical. Okay, so we add it to both sides. So we isolate the radical. Now we're going to square both sides because this is an index of 2, right? If it's not stated, if it doesn't show a number here, it's going to be an index of 2. So that means we're going to square both sides to get rid of this radical. Okay, so now we're going to get x squared is equal to 15 minus 2x. And now we can put this in standard form. And now we can try to factor this thing, right? And so this would be what? We have 3 and negative 2. Or no, I'm sorry. 3 and, no, 5 and negative 3. And so here are our factors. And now we're finished because we just have to solve for each one of these. And we get x is equal to negative 5 and x equals to 3. Now, x equals 3, no problem. Okay, x equal to 5, well, we're going to have a problem because we're going to get a negative under here. Can't have a negative under the radical, so it cannot be a solution. So the only solution is x equals 3. Now what about this one? Now we have two radicals, so we're going to have to end up doing this twice. Now we have to isolate one of the radicals. Doesn't matter which one, but we have to isolate one of them. So we can, why don't we add this one to both sides? And now we can get this. Now we're going to square both sides. And over here, we're going to have to use the FOIL method. Okay, over here, we're just going to end up with 2x plus 3. Okay. Now, don't forget the middle term when you square. Okay, don't forget this. Now, this is 2x plus 3. We get this. We get this. So be careful. Okay. Now, we're not done. Now we're going to do the same thing. We've still got this radical here. So now we're going to isolate this radical and do the same thing. So this is going to be x plus 1 plus 1. Okay. So what do we get? We get x plus 2. Right? And so then now we're going to bring it over here. We get x plus 2. And so we subtract 2 from both sides, we get 1. And we subtract x from both sides, we get an x. So we get x plus 1 is equal to 2x, 2 times the quantity, 2 times the square root of x plus 1. Okay, so now we're going to isolate again. So now we're going to divide both sides by 2. Okay. Now they went ahead and squared both sides, which is fine. You can divide by 2 and then square, but remember you got to distribute the square to this coefficient here. Okay. Okay, so that's what they did here. So you get 4 times x plus 1. Okay, so there you go. Okay, so now I'm going to distribute and put this in standard form. So distribution property, now we're going to put in standard form. And I get 2x minus, excuse me, x squared minus 2x minus 3 equals 0. Okay, and so now we can see if we can factor this. Okay, and so this is going to give what? 1 times negative 3 will give, added will give me negative 2. And so we get 1 and negative 3. And so x is equal to 3 and x is equal to negative 1. Okay, now negative 1 won't work. Okay, because we get oh wait a minute. No, negative 1's fine. Yeah, negative 1's fine. I'm sorry. Yeah, we just can't have negative. And this gives us what? This is 1. Let's see, negative 1. Yeah, this is fine. It looks like they're both fine. So we get x equals 3 and x equals negative 1, and they're good. So we have two solutions in this case. So x is equal to negative 1 and x is equal to 3 are both solutions. Now remember to isolate a radical in step 1. Okay, it would be incorrect to square each item individually as the first step. That would be a huge no-no. Okay, you cannot square each term individually to solve these. Okay, got to isolate one of the radicals first, then square both sides. So now here we go. So again, we would not want to cube this, and cube this. That would be wrong. What we want to do is isolate. Okay, if we're going to cube both sides, we have to cube the entire thing, which I would not want to do here. Okay, so what we're going to do is we're going to isolate one of the two radicals, and then we're going to cube both sides. Okay, so here we go. So now in this case, oh, this is awesome because there are cubes. If we cube both sides, both radicals go away at the same time. And so now look at that. Now I can put it in standard form and subtract x from both sides. And now here I go. now I have this. Okay, and so I can use the AC method or method of decomposition. And so this is going to give me 4. So what two factors of 4 will give me a negative 5? Well, it's going to be negative 1 and negative 4. That'll do it. And so I can use decomposition and I can solve for the factors x minus 1 and 4x minus 1. Okay. So again, make sure you use decomposition here because you get your two factors of negative 1 and negative 4. So you rewrite this middle term as x, minus 4x minus 1x, and then you do factor by grouping. If you have any questions, ask me in class. So now in this case here, we get x equals negative, x equals 1/4 and x equals 1. Okay, both are valid solutions, so they don't violate anything here. Okay, and the solution set is then 1/4, comma 1. So this is the solution set. Okay, don't get a negative value here, and this is positive. So this and this is going to be positive, so we end up with a positive. Oh, no, I'm sorry, I forgot. Cubes, these are cube roots. So there are no restrictions on the radical. I just realized that. Sorry about that. So odd roots have no restrictions, right? So it's only the even roots we have to watch out for under the radicand. Okay, now what about this one? Oh, so now we got rational exponents. So we got exponents that are fractions. So rational exponents or fractional exponents, same thing. So how do we solve this? Well, the idea is we want this power to be 1. Okay? Well, we're going to use the power property, the property of exponents of using a power to a power, right? So if we have this, okay, how would we solve this? Well, we're going to raise both sides to a power where this resulting power turns to 1. Well, if we use the power property, a power raised to a power, we multiply these. Well, what do we multiply by to give us a 1? Well, we always do the reciprocal. So we want to raise the power to a power of the reciprocal. And then we use the power property and we basically multiply powers. And that's going to give us 15 divided by 15, which is 1. And so now whatever we do to this side, we have to do to this side. And so we get 27 to the 5/3 power. So guess what? This is a perfect cube. 3 times 3 times 3 is 27. So we can rewrite this as 3 cubed, which will cancel with this 3. And then we get 3 to the 5th. And 3 to the 5th is 243. And so here's the way it works, right? Cube root of 27 is 3. 3 to the 5th is 243. Okay, so always look for those ways to simplify things. And so the solution set is 243. Okay, don't forget the curly braces when you're writing your solution sets. Okay, otherwise just say x is equal to 243. Okay, or you can say x is equal to and then separate commas if necessary. Okay, so now what about this one? Now so what we're going to do is we're going to basically raise both sides to the reciprocal of this power. Okay, so we're going to raise both sides to the 3/2 power. Okay, now why do we have the plus minus here? Because the index here is even. Okay, it's an even index, which means we're taking an even root of both sides. So you always have to have the plus minus here. Always. Okay, so now this is going to equal 1, and then we're going to have this. So we get x minus 4 equals plus or minus 64. Remember, well, what's the square root of 16? It's going to be 4, plus or minus 4. And then again, this is odd, so it doesn't matter, so we don't have to worry about this. So here, it's going to be plus or minus this squared, or this cubed, so it's going to be 4 cubed, which is 64. So we get plus or minus 64. So x minus 4 equals plus or minus 64. So we add 4 to both sides. And so we're going to get what? We're going to get 68 or negative 60. Right? We're going to get 68 or negative 60. Now, both solutions are good because here we're taking an odd root. So we're good. It doesn't matter. So we're not going to have any problem with these. Okay? So the solution set is x equals negative 60, comma 68, or you can write it in set notation like so. Okay, now, what about equations that are quadratic in form? That means that it has a form of a quadratic equation. So if we can do some sort of substitution where we end up with something that looks like this, where u is some algebraic expression, okay, but we're doing a u substitution. And of course, a can't be equal to 0, else this won't work, right? Then what we could do is we could use everything we know about quadratic equations and solving them, and then solve for u. And then when we're done solving for u, remember, we always have to put it back in the original variable. So let's look at this one. Now, here, we've got an x plus 1 here, an x plus 1 here, and notice this has a square up here, and this has a 1. Okay, so why don't I make my u substitution as u equal to x plus 1 to the 1/3 power. Then I'm going to get u here, and this is going to be u squared, and so I'm going to get u squared minus u minus 2 equal to 0, right? So that's exactly what we're going to do. Okay? So this is equal to this squared, right? Which is this is equal to the middle term. So it makes sense that we're going to use a u substitution. And now this is our new equation. So now we're going to solve this one for u. That's the first step. So this is easily factorable. So we know that u equals either 2 or negative 1. Right? So, but we're not done because we're not solving for u. We need to solve for x. So now what we're going to do is we're going to plug this back in for u here, and then solve again. So this is what we're going to do. Okay? Now, again, don't forget this step. Don't stop here because remember, if we start with x, we have to end with x. So now what we're going to do, we're going to now cube both sides. What do we get? Then we're going to get x plus 1 equals 8. And we're going to x plus 1 equals what? Negative 1. Okay, and then we're going to subtract 1 from both sides. We get 7 and negative 2. And then we're done. Okay? And that's the proposed solution set. Okay? Make sure you always check your solutions to make sure that they work. Okay? In this case, they do. Right? And also make sure it also is good to check so you didn't make an mistake in algebra. Okay, now what about this one? Well, now this one's negative values. Well, we don't want negative values. But how can we put this using a u substitution? Well, this is double this, right? So you could write this as this squared, right? So our u substitution is going to be u is equal to x equals negative 1, x to the negative 1 power. Okay? So again, we put in standard form, and again, just like I said, it looks like it's in quadratic form. So here, again, we're going to make u equal to x to the negative 1 power, okay? And then u2 is equal to the x to the negative 2 power. So we get 6u squared plus u minus 2. And so now we could use the AC method of finding the factors of this thing, right? And then using a method of decomposition, if you will. And we find that the factors are going to be this. And so we can solve for u easily in this case. But remember, we need x, right? We started with x, we need to finish with x. So now we're going to substitute back in for u, okay? So now we got to put this in terms of x again, okay? Now, well, this is a reciprocal, right? This is 1 over x. So in order to find x, we're going to flip these. So in this case, x is equal to negative 3 halves, or x is equal to positive 2. Okay? And again, make sure you check in the original equation to make sure that they work. And in this case, they do. And this is going to be your solution set. Now, when using a substitution variable in solving an equation that is quadratic in form, do not forget the step that gives the solution in terms of the original variable. Okay, so you always want to go back to the original variable that you started with. Don't stop prematurely. Okay, so let's look at this one. So now here we have what? We've got x squared and we've got x to the 4th. Well, this is this squared. So let's make u equal to x squared. Right? There we go. So let's make x squared u. So now we've got this formula, right? Now, this is going to be 24. Are there two factors of 24 that will give you a negative 11? I don't think so. Right? 2 times, so 24. What are the different factors of 24? Okay. Well, 24. Oh, yes, there is. Yes, there is. I'm sorry. There is. 3 times 8. So negative 3 times negative 8 will do it. And then you can use decomposition. So you can rewrite the middle term with negative 8u plus negative 3u, and that'll work. And so, yes, you can get the factors. So here's your factors. Okay. And so now you're going to solve these using the zero product principle again. And so we're going to solve for u. And so you get u equals 2/3 or u equals 1/4. And again, now we got to go back to what u is. U is defined by x squared. And so now what do we have to do? We have to take the square root of both sides. So this is going to be plus or minus the square root of 2/3. This is going to be plus or minus the square root of 1/4, which actually turns out to be the square root plus or minus 1/2. Okay? And so now remember, we don't want radicals on the bottom, so we want to rationalize the denominator. So we're going to multiply the top and the bottom by the square root of 3. So this will become 3 up here, and this will become the square root of 6. So we get plus or minus the square root of 6/3. And so this is our final answer here, and this is our final answer. So we actually have 4 possible solutions here. Plus or minus the square root of 6/3, and then we also get plus or minus 1/2. Okay? And so this is our solution set. Now, some equations that are quadratic in form are simple enough to avoid the substitution altogether. So to solve this one, so this was the one that we just saw, we can see that this can be seen as just 3x squared minus 2 times 4x squared minus 1, and then solve it directly using the zero product principle. Okay. Which method to use is personal preference. Okay, so if you like the use substitution method, go for it. If you can see it without having to use the substitution method, go for it. Okay, so that's the end of this section. Again, practice, practice, practice. Write down your questions, take notes. Make sure you watch these before the class period. Very important. Other than that, talk to you later. Have a great day. Bye-bye.